All right, we're discussing implicit differentiation. Now the question is, why do we need implicit differentiation? All right. If you notice it, all the examples we've done so far, so when we did the power rule, we did the product rule, the chain rule, the quotient rule, the, most of the function that we saw, or at least all the functions that we saw, were given in this form, all right? So where one variable is defined explicitly in terms of another variable. So y equals to some function in terms of x. You can see it here, y equals to x and x. But now the question is, what happens if I give you something like this? So x squared plus y squared equals to 25. Uh, to make it even complicated, I give you something like x cubed plus y cubed equals to 6xy. You see, in this case, you can explicitly write y in terms of x. It doesn't work, all right? So another way of saying that you can explicitly explain one variable in terms of the other, you can make y the subject, right? For this first one, if you make y the subject, you end up with some plus or minus, all right? And for the second case, if you notice it, you can make y the subject all because there will be some y that doesn't disappear. So for such kind of function, you're going to use implicit differentiation. So I'll repeat again. If you can make y the subject, so you cannot explicitly write y in terms of x or one variable in terms of the other, the first thing that comes to mind is implicit differentiation. All right? Take note, in a test, I would not say use implicit differentiation. You need to know what to use. All right, for the first function we saw, that was just an equation. So let me go back. So this first one here, this is just an equation of a circle with radius of 5. All right. If you try to make y the subject, notice it, you end up with something that looks like this. All right. So you end up with the plus or minus square root of 5 minus x squared. It means you can have two pieces. So you have the positive part and as well as the negative part. All right. And each of these are going to represent a portion of that circle. So let's look at the next slide. Notice it, the positive part represents a semicircle there at the top of the x-axis, and the negative part is just a semicircle on the bottom of the x-axis. All right. And the second function we saw is called the volume of Descant. It's very complicated, all right? Um, These are just some examples of this function. So if you replace this function f of x by some variable or some different kinds of function, you can get this piece that you see here. All right. So you notice it where we can just say, oh, y equals to something. So they're so complicated. Now where we're going to see the concept of implicit differentiation. All right. And how does implicit differentiation works? Let's look at the first example. It's very easy and straightforward. Trust me. The first one, x squared plus y squared equals to 25, and I ask you to find dy dx. Now you can see that just by inspection, you see that you need to do implicit differentiation, and you just need to apply d dx on both sides. So look at the solution here. All I do is to apply d dx on both sides. So differentiate both sides, all right? And you see I keep everything in brackets. Now split out the derivative, so you have d dx of x squared, d dx of y squared. Obviously, if you differentiate a constant, you get a 0. And there's another interesting thing you need to keep in mind. Whenever you differentiate a y, when doing implicit differentiation, you need to apply the chain rule. So you need to add an extra dy dx. This is a trick that you must remember for you to get full marks when it comes to implicit differentiation. Is that when you differentiate a y, for example, we have a y squared there. You see what I'm doing? I'm doing dy squared dy, and I say dy dx. So I end up with 2y, and then I have dy dx. All right. Why do you do that? Because y is a function of x. So you can't treat it as a constant. All right. So very important again, whenever you differentiate the y, you differentiate it using power rule as usual, but make sure you include the dy dx always. All right, that is chain rule now. And so that derivative, you get something like this. And if you make dy dx the subject, you just get minus x over y. Right? Part B, they ask you for equation of the tangent at a given point. I'm sure everyone is happy to do that. Remember that the slope of a tangent is just the same as the slope of your graph at that point. So dy dx that you found before is the same as the slope of the tangent line. So all you needed to do is to substitute the value of x and y in that dy dx that we found before. You get minus 3 over 4. That's the slope of a tangent. Obviously, if you use the equation of a straight line, y minus y1 equals to m into x minus x1, you get the equation of the tangent line. All right, straightforward and easy. All right, there's a solution 2, which I wouldn't recommend you to use this solution 2 at all. Is that someone can start by making y the subject. You see, get plus or minus. You identify the fact that at the point 3, 4, you're looking at the positive piece here, all right? Because x and y are positive. So you're looking at the upper semicircle. So you're not going to use plus or minus anymore. You're just going to use the plus part. And obviously, if you differentiate that function to find the slope, you get something that looks like this. And if you substitute x equals to 3, you get the slope at the point x equals to 3 to be minus 3 over 4. You see, you get exactly the same answer. And obviously, use y minus y1 equals to m into x minus x1. You still get the equation of tangent. Please stick to method 1, where we differentiate implicitly. We make dy dx the subject, and then we substitute the value of x and y to get our slope. And then we use the equation of a straight line to find the equation of a tangent. All right, straightforward and easy. Now let's look at other examples. Now I say find dy dx. I give you x cubed plus y cubed equals to 6xy. Again, if you see they don't panic, just apply dy dx on both sides, split out the derivative, and then apply the rules that I mentioned before. So notice what happened. My first step, which I want to see, please don't skip steps. You notice it, implicit differentiation usually carries a lot of marks, meaning that I need to see every possible step, all right? So first step is you apply d dx on both sides, all right? Second step, you see they have split the derivatives. If you differentiate x cubed, it's just 3x squared. If you differentiate y cubed, like I said, you apply the power rule, 3y squared, but you must include a dy dx. Why? Because y is a function of x. And to differentiate this, remember that is the product rule, because xy is product rule, all right? So you keep x, you differentiate y, you just have dy dx, plus you keep y, you differentiate x plus 1, all right? There we go, product rule. And the next step is you need to group, so here I just multiply out, and then I divide all through by 3 to get the step. And then take everything containing dy dx on one side and everything else on the other side, all right? And then factor out the dy dx and show me that you get this result. You see, when you do implicit differentiation, your final answer there for dy dx, you end up having x and y to tell you that you actually do implicit differentiation, all right? Now let's look at this example. This is the one that most people struggle with, all right? Similarly, I just applied d dx on both sides. And now you need to be very careful, because this function is not as straightforward as easy. If you differentiate sine of x plus y, you need to apply the chain rule. So first thing, you differentiate sine, which I get cos. You see, that's the derivative of sine, is cos. And then I have the derivative with respect to x of the inner function. All right, this inner function, that is called chain rule. This side, everyone knows what to do, is just the product rule. All right, this is the product of two functions, therefore it's product rule. So I keep y squared, I differentiate cos x, which I have minus sine x. Now I keep cos x and I differentiate y squared, which I get 2y dy dx. You see, whenever you differentiate y, you include dy dx. Most of you forget about the x and dy dx, and trust me, your final answer is just going to be wrong. All right. And then here, we keep this in brackets. If you differentiate x plus y, obviously if you differentiate x, you just get 1. If you differentiate y, you get 1 times dy dx. Again, we must include dy dx whenever you differentiate the y. This side, there's nothing to do. Now, this step here is me grouping every term containing dy dx on one side and taking everything else on the other side. Finally, factor out dy dx and divide all through to get your final result. All right, very, very important. So go practice. There's a lot of examples at the back of the textbook on the exercises for this section. Go do a lot of examples and get used to implicit differentiation. All right, because definitely you're going to get an implicit differentiation question. Now let's look at the derivative of inverse trigonometric function. All right. Now if I give you a function y equals to sine inverse of x, in other words, it means that sine of x equals to sine of y equals to x. Remember, if y is sine inverse of x, it means that sine of y is equals to x. So please remember that. And remember, for your sine function to have an inverse, we restricted a domain between pi over 2 and minus pi over 2. All right, that's why you see us stating this here. All right, so for the sine function to have an inverse, we want it to be 1 to 1. And the only way to make a sine function 1 to 1 means for it to pass the horizontal line test, we restricted the domain between pi over 2 and minus pi over 2. Now, how do we get the derivative of sine inverse? Is by looking at the derivative of this piece here. So we focus on sine of y equals to x. All right. So if you differentiate that implicitly, all right, so we're going to differentiate implicitly. If I differentiate the left-hand side, you agree I get cos y dy dx. Again, because this is a function in terms of y and not necessarily in terms of x. So if you see sine y, don't treat it as a constant because you're just going to get 0, which doesn't make sense, all right? So you differentiate implicitly, you apply the chain rule. So differentiate sine y, you get cos y dy dx. And right-hand side, if you differentiate x, you just get 1, all right? Why are we doing that? Because if I make dy dx the subject, I get 1 over cos of y, all right? But you're not done yet. Remember, there's an identity that says cos squared of y plus sine squared of y is equals to 1. I'm sure everyone is familiar with that identity. And if you make cos y the subject from that identity, you end up with square root 1 minus sine squared y. Remember, we don't have plus or minus because within this interval, cos of y will always be positive. All right. And if you have square root 1 minus sine squared of y, you go back to what we were differentiating before, which is this guy at the top. Sine of y is just equal to x. Therefore, I can, everywhere I see sine of y, I can just put x. I end up with square root 1 minus x squared. All right. Therefore, as a summary, we say dy dx is equals to 1 over square root 1 minus x squared, which is what you see there in box. All right. If you follow the same idea to differentiate tan inverse of x, you end up with something that looks like this. And this table here, guys, is a must know. You must know these guys here. Very, very important. All right. If you see an inverse, so I ask you to differentiate the sine inverse and cos inverse, please do me a favor and just state this answer here. Don't go through that whole that we saw before. All right. So in the test, if I say differentiate maybe x times sine inverse of x, just apply put the rule, and when you differentiate sine inverse, just state this answer, for example. All right. Don't go show me the whole process of where this answer is coming from. Just use them directly from the table. All right. Let's look at some example. Differentiate y equals to 1 over sine inverse of x. Oh, guys, there's something I need to mention, all right? For my years of lecturing, there's something that has changed. Students don't see this as sine inverse, they see this as some sort of reciprocal. I don't know. If you see sine to the power negative 1, that is not reciprocal, all right? That is sine inverse. It's the same as arc sine, not 1 over sine. Many of you guys see that and you say you convert that to 1 over sine for some reason. Please don't do that, all right? If you have a number raised to the power minus 1 or a variable, let's say x raised to the power minus 1, yeah, we mean 1 over x, all right? But not a trig function. A trig function, and you see this minus 1 here at the top, please, that minus 1 stands for inverse, not reciprocal, all right? So in this case, we have the derivative with respect to x of sine inverse of x. You now see the 1 there at the top. The reason why I put this example is so that you see the difference between inverse and reciprocal. If I give you a trig function and I want to deal with reciprocal, I'm going to explicitly write 1 over something, all right, to show you that it's reciprocal, all right? But if you see me just saying sine inverse, please, it's inverse. So this minus 1 there on top of your trig function is the inverse, all right? This extra minus 1 you see here is now the reciprocal, all right? If you apply the chain rule, obviously differentiate the outer function, and you have to differentiate the inverse function. Notice it, I just did the answer for the derivative of sine inverse of x, all right? I didn't show that whole process that we did in the beginning to prove what the derivative of sine inverse. Please don't do that in the test, you'll be wasting your time. All right, for B, we need to differentiate x times arctan. All right, very important. Arctan means tan inverse. It looks like some of you don't know what arc means. When I say arc sine, arc cos, arctan, it means the inverses. All right, so it's the same as saying x times tan inverse of root of x. Very, very important. That's why I put it here so that you can see and you remember. Now, how do we differentiate this? You can see there's one function there, which is x. There's an x, and there's another function, which is the arctan function. That's a product, all right? Therefore, we need to apply product rule. We keep x constant, we differentiate arctan, so you just go plug a table. Please remember your chain rule. You have 1 over 1 plus root of x squared, but you need to differentiate the root of x, all right? So that is chain rule that we're doing there. And product rule says you keep the other function constant and you differentiate the other one, which is now x. If you differentiate x, you just get 1. And you're done. You stop there, all right? Beside MCQ, where I'm going to simplify the answer and you need to choose which one is correct. If I ask you in a test, you get to this a step like this, please don't try and rationalize or do some funny stuff, all right? Just stop there if you can't simplify any further. Now let's look at derivative of logarithmic function. Now this table here at the top, again, you try and remember that as much as you can. The derivative of log of x, this b you see is the base, all right? Derivative of log of x to the base of b is just equals to 1 over x ln of b, all right? And the nice proof there for you to see. Now, if I change the base to e, remember that is now called ln, all right? So ln is just log to the base of e. And the derivative will just be 1 over x. Why? Because ln of e is just 1. So if you say 1 over x times ln of e, remember ln of e is just 1. That's why I end up with 1 over x. Now be careful. If you have ln of some function, then you need to do chain rule. All right. You can see in this case we have derivative with respect to x of ln of u. All right. Here we are assuming that u is a function of x. So if you apply chain rule, you have 1 over u times du dx. All right, this one is even more clear. If you have derivative with respect to x of ln of g of x, you see here I'm showing you clearly that ln of some function, all right, not just x with coefficient of 1 and a power of 1. This is now some function g of x. You need to apply chain rule. So you say 1 over g of x times the derivative of g of x. All right. So always think about chain rule. Let's look at some example. I ask you for the derivative of ln of x cubed plus 1. Like I said, you're going to get 1 over the function, which is x cubed plus 1. Chain rule, you need to differentiate the inner function. If you differentiate x cubed plus 1, you have 3x squared. And if you simplify, you get this, all right? There's no need to show me this whole process here, all right? As long as I see that you're applying chain rule, I'm more than happy. Look at this one as well. This is also chain rule. The derivative with respect to x of ln of sine x, already you know it's going to be 1 over sine x times the derivative of the inner function, which is sine of x, and that's why we get cos of x. Cos of x over sine of x is cot of x, all right? Please don't be so negligent and just leave it as cos of x over sine of x. We know what cos of x over sine of x is. Just say cot of x so that you get the full marks. Another example, now we have the root of ln of x. Now I mentioned something. If I say differentiate the root of a ln function, please just write this as ln of x to the power half, all right? Root always means power of a half, all right? Now, what is the derivative? You see that we start by applying the power rule. We differentiate the outer function, so it's half into ln of x to the power minus half. And then chain rule applies, meaning that you need to differentiate the inner function. In this case, what is under the root is a ln function. You differentiate ln, which is just 1 over x, all right? And if you simplify, you get this result. Go practice to do many examples. The only way you're going to figure this out is to do a lot of examples. Another nice example now is this one. I said differentiate log, all right? Log base 10, 2 plus sine x. We've already seen it's going to be 1 over the function inside the log, which is just 1 over 2 plus sine x. And then you need ln of the base, all right? The base here, I mentioned it is 10. And obviously, you have a function, that means you need to apply chain rule. So you need to differentiate that function inside the log. And if you simplify, you get this, all right? I need to mention something. If I say log and I don't mention any base, automatically base of 10, all right? Don't ask me in a test that what base is this or assume another base. If you don't see any base, it means base of 10, all right? If the base is e, I'm going to just call it ln, all right? If there's any other base, I'm going to specify what that base is. But if I don't mention any base, it means it's base of 10. Another nice example. Now this is where things get a little exciting. You have d dx of ln of some algebraic functions. You have this polynomial over some root function, all right? How do you differentiate this? Obviously, if you follow the old technique, which is 1 over anything that's inside the lane, and then times the derivative of that function inside the lane, yeah, that's a lot of maths and simplification, but somehow you get to the final answer. But you see, there's a lot of work here in between, all right, which you can easily make a mistake. The reason why I put the example is so that you take note, all right? Because the next example or the next solution is what I want you to do in my test, all right? If I give you derivative with respect to x of ln of some complex function, I expect you to start by simplifying that complex function, all right? You know the laws of logarithm. Ln of a over b is ln of a minus ln of b. Just apply the laws of logarithm there. You see it becomes easy to differentiate, all right? And simplifying this also becomes easy. Look at the previous solution. You see, you have to multiply this whole thing by some quotient rule. You need to factor out common terms. You need to simplify and then get to this. This is a lot of work. So please simplify your logarithmic function, the laws of logarithm, before differentiating, all right? Because when you differentiate this, it's easy. You know, it's just 1 over x plus 1. Here it's just 1 over x minus 2 done. And that brings us to one of the most important examples of the day. Guys, this example, I'm not sure if it's very clear. Please go download the PowerPoint slide and look at it. It's example 7 in your textbook. Is y equals to x to the power 3 over 4 times square root x squared plus 1 all over 3x plus 2 all to the power 5. You see, this is a very complex function. Once you see this, you need to apply the rules of logarithmic differentiation. All right, logarithmic differentiation applies here. All right, what do we mean by logarithmic differentiation? Your first step is to try and simplify this complex function by applying ln on both sides. You can see here, I say ln of y, and if I apply ln on this side, it simplifies to 3 over 4 ln of x plus half ln of x squared plus 1 minus 5 ln of 3x plus 2. All right, apply ln on both sides. Use the laws of logarithmic to simplify the right-hand side as far as possible. For you to get the final answer correct, you have to simplify as far as possible before you start differentiating. All right. For example, if you have root like this step here, you have root of uh, ln of root of x squared plus 1. Please take the power of half in front of the ln. All right. Again, here, if you have ln of x to the power 3 over 4, take the 3 over 4 in front of the ln. All right. Once you simplify it as far as possible, so that the powers here, you see the power here is 1, the power here is 1, the power of x here is 1, you more than welcome to start differentiating implicitly. All right. Implicitly, if you differentiate y, you have 1 over y dy dx. I've seen a lot of funny answers before. Some people just say y and that is it. Some people just say dy dx. Please, when you differentiate ln of y, obviously get 1 over y. And because, like I said, y is a function of x, you need to apply chain rule. You say dy dx. The right hand side, you differentiate. And take note here, if you make dy dx the subject, this y comes here. Surprisingly, 70% of the class always stopped here. I don't know why they stopped there. It's like they like giving me why in the final answer. I'll mention it today. If you see logarithmic differentiation in the test, I'll do you a favor even to tell you that use logarithmic differentiation to differentiate this function. For those of you who know what logarithmic differentiation is, good luck, because if you use any other method, I'll give you 0, all right? If I ask you to use logarithmic differentiation to differentiate the function, you need to follow all these steps here, all right? Apply ln on both sides, simplify the right-hand side using the laws of logarithm as far as possible so that the functions, they always they have power of 1. Then you can go ahead and differentiate. Once you reach this step, you're not yet done, all right? If it's out of 5, you just have 4. I'm going to ask you, what is y? You need to go back and plug this whole y that you see there. You see what I'm doing here? I need this final step. So my dy dx, you see, it is completely in terms of x. So if I see y here in your final answer, it means you're not yet done simplifying. I'll repeat again. Don't stop here. I've done that before, and many people stop here. They think they're done. You're not done. Substitute what this y is. So put the entire function in there and just leave it like this. Please don't multiply out. Just leave it like this. You get your full marks. All right. That's the last slide.